Hi class. Okay, so today is going to be the second part of our gas laws lecture. So in the previous lecture we covered Charles's law and Boyle's law. Today what we're going to be talking about is Gay-Lussac's and the combined gas law. So we're going to kind of throw everything together and finish this up and wrap it up nicely like a cute little bow. Alright, so what I wanted to do first is to kind of emphasize what the situation is going on right now in reference to the problems that you're solving. So what it is that say that I blew up a balloon, okay? Would you agree that it has a specific volume, a specific pressure, and it's probably at a specific temperature, okay? That would be condition one. Well, let's say that, we'll use Charles's law for our example, okay? Let's say that it has the very specific volume, and we'll say that it has 273 Kelvin, okay? But what happens if I add some heat to it, okay? Ignore my ugly fire, just imagine that being a fire, and I raise it up to about we'll actually say about 350 Kelvin, okay? What would you expect to see based on Charles's law? If I increase my temperature, what do you expect the volume to happen? Very good, you would expect an increase, which, as my lovely picture shows, would actually happen. But the thing is that it's still the same balloon, okay? I haven't changed. I didn't put it anywhere else, or I haven't grabbed a new bottle. It's still the same balloon. All that happened is that my volume expanded. I had a very flexible container, so that way, as my temperature increased, my volume could expand to compensate for that increase in motion. Okay? So as you can see, this guy's volume is about this size, and it increased as I increased my temperature. We'll say like 273 to 2, okay? So just keep that in mind, that it's still the same balloon. What you start with is what you end with in reference to how many molecules you start with. However, your volume was very flexible, so that way it could expand without compromising anything, okay? So just to review, we talked about two different laws. We talked about Boyle's law and we talked about Charles's law. So remember that Boyle's law has an indirect relationship. So as one goes up, so say the pressure goes up or increases, what happens to the volume? Very good, it decreases. Make sure you understand that, because that's definitely something that I'm going to be testing you on. Alright, same thing with Charles's law. However, Charles's law, does it have a direct or indirect relationship? Very good, it has a direct. If you increase the volume, what's going to happen to the temperature? Very good, it's going to increase as well. So it's a very good tool to double check your answers to make sure that everything's cool. Alright, everything's copacetic. So let's go ahead and learn some new stuff, okay? So the first thing that we're going to be talking about is the Gay-Lussac law. Alright, and so it states that the pressure of a given mass of gas varies directly with the temperature at constant volume, okay? So just like how Charles' law was had a direct relationship between volume and temperature, Gay-Lussac has it, but between pressure and temperature, okay? So let's complete this sentence. An increase in pressure would cause a blank in temperature. Do you think it would increase or decrease? Very good. It would cause an increase in temperature. Now this is specifically why I tell you that you should write out what variables you have, because you'll notice in the next problem that I give you, instead of giving you V1 and T1, I would be ended up giving you P1 and T1 as your variables. As soon as you see this, you should automatically think, oh, okay, so I'm going to use this law instead of the other one, okay? So let's go ahead and look at a problem. As you can see, I have a helium gas in a 2-liter cylinder that is under 1.12 atmospheres of pressure. At 36.5 degrees Celsius, the same sample of gas has a pressure of 2.56 atmospheres. What is the initial temperature of the gas in the cylinder? Okay, as you can see, even though it does mention a volume, do you see that the volume doesn't change? So my volume is constant. So we know that we're not going to use Charles's law. Okay, we can cross that out. But I do have an initial pressure 1.12. I do have a final pressure, or P2, which is, very good, 2.56. And don't forget to write the units. And I also have a temperature. However, who does he correlate with? Do you think that he belongs with the 1.12 atmospheres or the 2.56? All right, very good. He actually belongs to the 2.56, okay? So remember, it says at 36.5 degrees, the sample of gas has a pressure of 2.56. So he's not T1, he is T2. All right, which means who are we going to be looking for? Very good, T1, okay? Now remember, I can do this. I can give you any set of variables and ask you to solve for P1, T1, P2, T2. It does not matter because the same law is going to be put into effect, so you should be able to solve this, okay? So let me grab out my handy-dandy whiteboard. And let me go ahead and erase this to create a little bit of room. Now, what's the first thing that I need to fix? Because before I start anything, before I plug and chug, what do I need to fix? Very good. I need to fix my temperature. So what do I need to do? Add it to 273. So that's going to come out to 309.5 Kelvin. Okay? So that is my new T2. All right? So now that I have all my ducks in a row, I'm able to actually plug it in. So my equation is P1 over T1 equals P2 over T2. Alright? And so, like I said, by doing this, all you actually have to do is just plug and chug. You just plug all your different variables in and see what number you can get. Okay? So let's go ahead. For P1, that's going to be 1.12 atmospheres over T1, because remember that's what we do not have. I have 2.56 atmospheres over 309.5 Kelvin. Remember, everything has to be in Kelvin. So what I usually do, I'm not sure how you guys do, whatever way is best for you, I cross multiply. Okay, so in this case, I have 1.12 ATM times 309.5 Kelvin equals 2.56 ATM times T2. Okay, and then how do I isolate my variable? Very good, you just divide both sides by 2.56. And so my T2, put it up here, is going to be equal, or I'm sorry, not T2, woo, see, even I catch myself. T1 is going to be equal to what? Very good. Approximately 136, maybe 135 depending on your calculator. Okay? So this is going to be my answer, which kind of makes sense because think about it in reverse, okay? So my pressures are increasing, so you would expect that your T1 should be smaller, so that way it would allow an increase in temperature, which it does. Okay? So, to continue on, the second one that we're going to talk about is the combined gas law. Now, this one just combines all the three different laws, Boyle, Charles, Gay-Lussac, all of it, all put into one beautiful equation, which is the combined gas law, which is just P1 times V1 divided by T1. Okay? And so this is just the one that you use when you say that nothing is constant. If you remember and you look back, all of these say that something is constant, right? If you look at here, this one had a constant volume. If you look at any of these, Boyle's law had a constant temperature and Charles had a constant pressure. So all of these had something that was constant. The combined gas law is used when nothing is constant, okay? And you can still see the same direct and indirect relationships between these. Okay, you can see between there there, and there. All the direct and indirect are still in play. However, it's just a bigger equation, okay? So let's go ahead and try solving for a problem. As you can see, this is when you would need to label especially all of your different variables, because once you realize that all three variables are in play, you can see that this is the law that you're going to use. So go ahead and write it out. Include all of the variables that you already have, and then identify which is the one that we're trying to find. As you can see, the question is asking this: what is the new volume? So that means this guy, V2, is what we're going to be looking for. So to save on time, I'm just going to autofill it. So what I did is that I highlighted all of the conditions that fall under for 1, and all the conditions I highlighted for 2, and follow this respectively. If this is what you got, then good job. If something would arrive, then come see me after class and we'll see where your confusion is, okay? So what we're going to do is we're going to go ahead and solve for it. So, like I said, the equation that we're going to be using is P1 V1 over T1 equals P2 V2 over T2. Now I'm going to go a little fast because I'm going to run out of time soon. So just keep going, or just pause me if I'm going a little too fast, okay? So like I said, just plug in your variables. For P1, it was 110 kilopascals times 2 liters, because that was my volume, over my temperature. Now remember, the temperature was in 30 degrees, so what do I need to change it to? Very good. I need to change it to Kelvin, so 303 Kelvin, and then the same thing over here, which should be 353. So once I plug that in, 303 Kelvin is equal to 440, and I'm looking for my volume. That should be kilopascals, and that should be 353 Kelvin. So just like how you did before, you're going to cross multiply. It just might be a little bit crazier with the math. So how it should end up looking is 110, might look a little crowded too, times 2 liters. And so I multiply both sides by 353, and I divide both sides by 440 kilopascals. Now, like I said, the cool thing is that everything, all the units cancel out. And so you know you did it right, because what's the only one that's left is the liters. Very cool. Which means that after you do all of this, my volume is going to be about 0.58 liters. Okay, which should make about sense because you have a little bit of decreasing, a little bit of increasing, okay? Especially a lot of increasing, especially on your pressure. So that's going to cause a serious effect on that. Okay, so we're going to work on some more problems tomorrow. So hopefully this was helpful. And I will see you in class tomorrow. Okay, bye.